Today, we are going to review the AWS Solutions Architect Associate SAA C03 sample questions that are available on the AWS certification homepage. In my previous video, I talked about the advantages of going to a test center and solving problems visually. I'm going to show you some examples today. Here's the first question. Now, if you're taking the test at home, this is all you will see on the computer screen. You would need to absorb all the information presented here and select the answers. On the other hand, if you go to a test center, you can draw some visuals on a writing pad provided by them. So we're going to try both these approaches. So I'm going to ask you to pause the video now and see if you can answer the question. And don't use any paper and pencil. And continue once you're ready with the answers. If you are at a test center, you can capture this information using diagrams. Let's see how this approach would work. Now, instead of a paper, I will draw on PowerPoint as it will be nicer and easier to share with you all. A company has a 3-tier app in a VPC deployed across multiple availability zones. When you see 3-tier, usually it means web, app, and database tiers. The app tier EC2 instances are in the private subnet. So let's draw a line separating private and public subnets. The app servers need to download software from the internet. However, app instances must not be accessible from the internet. Now, from this requirement, you might have already figured out what the answer is. We need a NAT. NAT allows private instances to send outbound requests to the internet, and it also blocks unsolicited inbound requests. But the question here requires us to select two choices. So let's look at the options. Let's look at choice A, configure NAT gateway in the public subnet. This choice is valid. Now, choice B talks about a custom route table. Let me show you a visual from my Solutions Architect preparation course. I've shared the link to the material in the video description. This VPC layout shows how to configure routes for public and private subnets. The public subnet route table allows all local traffic, and the non-local traffic is routed to the internet gateway. Whereas the private subnet route table allows all local traffic, and here all the non-local traffic is routed to the NAT gateway. So when you add a NAT, we need to update the private subnet route table to ensure internet-bound traffic is routed through the NAT gateway. So choice B is also valid. We already got two correct answers. Let's review other options to make sure we are not missing anything. The elastic IP is not required here. And choice D uses a custom route table with a route to the internet gateway attached to the private subnet. This choice is incorrect as it will change the private subnet into a public subnet, because it's now going to have a path to the internet gateway, so it will become a public subnet. In addition, this change would also allow inbound requests from the internet. So clearly this is not the way we want to do it. And choice E asks you to place the NAT in the private subnet. Now NAT needs to be in the public subnet. So this choice is also incorrect. So the correct choices for this question are A and B. So what do you think here? Do visuals really help? If it does, keep this in mind when deciding where to take the test. So let's continue with other questions and answer them using diagrams. Question 2. Here, we need to design a solution to save costs for EC2 instances that do not need to run during a 2-week shutdown. So why can't we just stop the instances? What are we missing here? So here comes the next requirement. The application stores the data in instance memory, and they must be present in the memory when the instances resume operation. So we are required to restore the memory state. So when you do that, instance can continue from where it left off. This type of pause and resume capability is provided by hibernation. Let's look at the choices. Choice A talks about using instant store volumes. Now these are temporary volumes and we will lose the data when the instance is stopped. So this does not meet the requirements. A snapshot is an option, but before you snapshot, all application data must be flushed to the volume. But when you restore a snapshot, you're going to create a new instance. So this option will not restore the instance memory state. So this is also not a valid choice. Choice C asks you to run application on instances that support hibernation. So we need to hibernate the instances before the 2-week shutdown and restart them later. This will wake the instance up and restore the memory state for us. Now from cost perspective, when the instance is in hibernation, we only need to pay for the storage costs. So this choice in fact makes sense. So this is a valid choice. Now let's look at the next choice. This talks about noting down availability zone for each instance and then restarting in the same availability zone. If you think about it, this is the default behavior. And we cannot change the availability zone of an existing instance even if we want to. So this choice is also invalid, as stopping and restarting the instance will not restore the memory state. Choice C is the correct answer for this question. The next question is really long with a lot of details. These type of questions are in fact easier to work with paper and pencil at a test center. Here we have a monitoring application on an EC2 instance, and connections are made to the instance using private IP. We need to design a solution that will redirect traffic to a standby instance if the app fails and is unreachable. Now, to redirect to a standby instance, we need to ensure the standby instance is assigned the same private IP address that was used by the primary instance. This requirement can be met by attaching a secondary elastic network interface. The primary ENI stays with the instance for the life of the instance, but the secondary ENI can be detached and attached to a different instance. The IP address that is associated with the secondary ENI also moves to the new instance. Let's look at the answer choices. Choice A talks about load balancer. A load balancer is typically used when all instances are in active mode. Here, this question talks about a failover configuration. Only the primary instance receives all the traffic, and standby is used only when the primary fails. There is also no indication if the app is a web application. So ALB is not really a valid choice here. Choice B talks about configuring a custom DHCP option set to assign the same private IP address to the standby instance when the primary fails. Now the DHCP service dynamically assigns IP addresses to the instances. It in fact has some customization option, but it gives you control over the domain name and a few other options. However, there is no provision to control the reuse of an IP address. So this choice is also not valid. Choice C talks about attaching a secondary elastic network interface to the instance. And when the instance is not reachable, we're going to move the interface to the second instance. This is exactly the option that we discussed earlier, so this is a valid one. Choice D uses an elastic IP address. Would this option work? In fact, you can use elastic IP address and assign it to a different instance if you want. So this option would also work. However, elastic IP is a public IP address. The requirement calls for a private IP. So among all these choices, C is the best option. Now, if you look back at this question, we captured the essence of this long question and its choices in a very simple diagram. So here we don't have to keep going back and rereading the question or the choices, because the diagram makes it very clear and easy to answer. On to question 4. An analytics company is planning to offer a web analytics service to its users. The users of the service need to include a JavaScript in their web page. And this JavaScript will make GET requests to the service's S3 bucket. We need to ensure the JavaScript executes successfully. The problem with this setup is domain names are different between the user's website and the analytics service. The browser, in fact, prefers to send the request to the same origin. When a JavaScript talks to a different origin, the browser will cross-check with the destination if such a call is allowed from the requesting domain. This configuration is called CORS, Cross-Origin Resource Sharing. And we need to ensure that the Web Analytics service has this configured to allow cross-origin calls. Let's look at the answer choices. Choice A looks valid. Choice B talks about S3 versioning. We don't need versioning for this particular question. A signed URL for the script may solve a different problem. The primary issue here is the cross-origin call. So this is also not a valid choice. Now, there is no execute permission for S3 buckets. For hosting scripts in an S3 bucket, we need to ensure the caller has read access. So among these choices, choice A is valid. So here's question 5. A company's security team requires that all data stored in the cloud be encrypted at rest at all times. So we need to ensure that data in the cloud is encrypted at rest. The catch is encryption keys are stored on premises. So the data is in the cloud, but the keys are on premises. When you have a situation like this, we have a couple of different approaches. We can encrypt the data on premises and store the encrypted data as is in the cloud. And when you attempt to read the encrypted data back, we simply get the data on premises and decrypt it there and on premises. So here, with this solution, encryption and decryption is performed on premises. Now, another option is we can include the encryption keys as part of the request to the cloud service. The service would then perform encryption of data before storing them. Similarly, a request to read the data must also include the key. The service would then use the key to decrypt the data. So in this case, the cloud service performs encryption and decryption using the key provided by the caller. Which two options meet these requirements? So choice A, S3 server-side encryption. Here, S3 manages all the keys and the keys are stored in the cloud. So this is not the correct choice. Similarly, choice B uses S3 KMS. Here also the keys are stored in the cloud. So this is also not the right choice because our requirement calls for maintaining the keys only in on-premises. The choice C, S3 server-side encryption with customer-provided keys will meet the requirement. Here, the caller provides the encryption keys when they make the request to S3. And with choice D, we are going to use client-side encryption. This is also a valid option. Data is encrypted and decrypted on premises. Now with choice E, it's asking us to use a Lambda function to encrypt data with customer keys. Now the problem here is data is stored unencrypted initially, and then Lambda goes and encrypts the data. So there is a time window when the data remains unencrypted. However, our requirement calls for encrypted storage, so this also does not meet the requirement. Among these choices, choices C and D are correct. Question 6. A company uses Amazon EC2 reserved instances to run its data processing workload. Here the job takes 7 hours and must finish within a 10-hour window. So what is the issue here? The month-end jobs are expected to take more than 10 hours with the current resources. So this is going to exceed the 10-hour time window we have. And also the job cannot be interrupted before completion. So this essentially rules out spot instances. But we also need a cost-effective solution to increase the resource capacity. So the key point here is we need additional capacity only for a few hours each month. Choice A asks us to use on-demand instances during periods of high demand. We can indeed use on-demand instances, and we need to pay only for the duration the resource was running. And with on-demand, the instances won't be interrupted either. So A looks like a valid choice. Choice B recommends buying a reservation for additional instances. Now, reservation is a long-term commitment for primarily 24/7 usage. However, here we need additional instances only for a few hours every month. So a reservation is wasteful and not the right solution for this question. Now, choice C recommends using spot. Spot instances cannot be used because there is a requirement that a job cannot be interrupted, whereas with spot, there is a possibility of interruption. So we cannot use spot. Finally, choice D recommends changing the existing reservation to increase the size of the instance. Once again, this change is a long-term commitment and not ideal when you need the extra capacity only for a few hours every month. So among these choices, on-demand instances, which is choice A, is the correct answer. Question 7 is really long. So let's focus on the problem. A company runs an online voting system for a weekly live television program. And during broadcasts, users submit hundreds of thousands of votes within minutes. The request is handled by a fleet of EC2 instances with auto-scaling. These instances then write the votes to an RDS database. The problem here is database is unable to keep up with the sudden increase in the load. So we need to come up with the most efficient solution that also does not need a downtime. Now the current architecture is tightly coupled. Any changes in traffic pattern requires us to scale all the layers. And any disruption in the database layer would also cause an outage. The solution for this situation is to use a loosely coupled architecture. For example, we can introduce a queue or streams. The web layer would record the votes in a queue or Kinesis streams. A separate process would then read the votes and record them in the database. This backend process can adjust the processing rate so that it does not overwhelm the database. So that will be our preferred option. So let's look at the choices. Choice A is asking us to migrate the front end to a Lambda function. However, migrating the front end is not going to help here because our issue is in the backend, not in the front end. Choice B asks us to scale the database horizontally by converting it to a multi-AZ deployment and configure the front-end application to write to both primary and secondary DB instances. Now, in case if you look at the question says that the system uses an RDS relational database. With a relational database, we have only one primary instance for write traffic. However, the read traffic can be offloaded to read replica. Our scalability issue is with database writes. We cannot scale horizontally with a relational database to support writes, as the writes are handled only by the primary instance. So this is not the correct choice. With choice C, we modify the front-end app to send votes to an SQS queue. The worker instances then read from this queue and write to the database. This solution is in fact perfect and it is the correct solution. Choice D recommends vertically scaling the database during voting periods and reducing the size after the voting ends. While this would work, the scaling action in fact requires a downtime. So this does not meet the no downtime requirement. So among all these choices, C is the correct solution. Question 8 is also a long one. A company has a two-tier application architecture that runs in public and private subnets. EC2 instances running the web application are in the public subnet. The EC2 instance for the database runs on the private subnet. So web application EC2 instances are in the public subnet, and a single database instance is in the private subnet. So note the use of a single EC2 instance for database. And all these instances are also running in a single AZ. So we need to come up with a solution that provides high availability. We need to pick two choices. So to improve availability, we need to spread out our infrastructure across another availability zone. For web servers, we can deploy additional instances in the second AZ. Similarly, for the database, we need to run a standby instance in the second AZ. Let's look at our options. So choice A asks you to create new public and private subnets in the same AZ. We don't need another public and private subnet in the same AZ. We need them in a different availability zone. Choice B recommends setting up an autoscaling group and application load balancer spanning multiple AZs for web instances. So this is a good solution. We need it. Choice C recommends adding existing web instances to ASG and ALB. This alone will not solve the issues for us, as we need to spread across multiple AZs. Choice D recommends creating subnets in a new AZ, which looks good. It is also asking us to create a database instance in the public subnet and migrate the data to this new database. Now, the database needs to be in the private subnet, and migrating data to another single instance database is not going to provide high availability. So this choice is clearly incorrect. Choice E recommends creating subnets in a new AZ, and it's asking us to deploy an RDS multi-AZ database in the private subnets. And finally, migrate the data to this new database. So this solution would also address the high availability requirements. So the correct answers here are B as in boy and E as in elephant. Now let's look at question 9. To be honest, I was very confused with this question. It took me a long time to figure out what they're asking. So I would have probably got this question wrong if I had seen this question in the exam. But I might have come to the correct answer using elimination. I might have eliminated all the other choices and still answered correctly. So that's another tactic that you can use. Here we have a custom web app that receives a burst of traffic at noon. And users are seeing timeouts when uploading pictures and content. The architecture uses EC2 instances in an autoscaling group. And when new instances are launched by autoscaling, the app requires an additional 1 minute to initialize. So what should we do to respond better and avoid the timeouts? The architecture appears to be scaling based on traffic. However, users are still seeing timeouts. So maybe the requests were sent to the new instances when the application was still initializing. So that's why they are seeing timeouts. So we need a solution that gives the instance sufficient time to initialize. Let's look at the choices. Configure a network load balancer with a slow start configuration. NLB is optimized for performance and it does not have a slow start mode. However, an application load balancer indeed has a slow start mode. By default, a target in an application load balancer receives its full share of requests as soon as it is registered with a target group and passes the health check. If you configure the slow start mode, ALB gives the targets time to warm up before it starts sending them the requests. So this choice would have been valid for the application load balancer, but not for NLB. Choice B is using Elasticache to offload requests from EC2 instances. However, the problem appears to be with EC2 instances when processing the incoming requests. If it is unable to even receive the request, it won't be able to forward it to Elasticache. By the way, there is also an answer explanation towards the end of the sample question PDF that AWS provides. But the problem is they don't talk about all the incorrect answers there. So that's one thing you have to work out. So hopefully I'm filling that gap here with this review. So choice B also appears to be incorrect. Now with choice C, configure an autoscaling step scaling policy with an EC2 instance warm-up condition. Autoscaling indeed has a warm-up parameter that allows additional time to initialize instances. Now, the instances in the warm-up period do not receive requests from the load balancer. So this might be an option to allow extra time for the instance. Let's look at choice D. This solution uses CloudFront and ALB. Now, CloudFront is useful if you see issues when reading data, as it can handle the requests using the edge cache. However, when uploading new content, CloudFront is going to forward it to the origin. So in this case, CloudFront is not going to reduce traffic to the origin. So we're still going to see the timeout. So among these choices, only C seems a viable option. So we're going to go with C. Let's look at the final question. An application running on AWS uses Amazon Aurora multi-AZ DB cluster for its database. Now, Aurora automatically replicates data across 3 availability zones. When evaluating performance metrics, a solutions architect discovered that the database reads are causing high I/O and adding latency to the write requests against the database. So the issue here is read traffic is interfering with writes and impacting the writes. So when you observe these kind of issues, what it means is that read and write traffic are all going through the primary instance. And the primary is not able to handle all the requests. In situations like this, we can either vertically scale the server or add read replicas to offload read requests. So let's look at the options. Choice A asks us to enable read-through caching on the Aurora database. Read-through caching uses a cache to answer queries, and when there is a cache miss, it will read from the disks. This might help, but most databases are already smart enough to use cache. And choice B talks about using a standby instance for reads. A standby instance is used only for high availability in a relational database. So we cannot just run a SQL query against a standby instance, because it is there for high availability, and what it means is when primary goes down, standby will be promoted as the new primary, and then we can fire SQL queries. And a second issue is that Aurora does not have the concept of standby instances. Aurora promotes a read replica as the primary when an existing primary goes down. Or in case if you don't have a read replica, it will launch a new replacement instance for primary. So this choice is also not valid. Choice C talks about creating an Aurora replica and modify the application to use the appropriate endpoints. This can definitely address the issues described in the question. And with choice D, it's asking us to create a second Aurora database and link it to the primary database as a read replica. This choice is incorrect. You cannot link 2 databases like this. So among all these choices, choice C is the correct answer. So with this 10 questions, we touched upon important topics related to the Solutions Architect exam. We talked about VPC, cost optimization, high availability, troubleshooting deployment issues, data security, and performance. And more importantly, we saw how drawing pictures could help you visualize and analyze and answer questions faster. In fact, you can use this approach if you go to a test center. However, if you take the test at home, you're out of luck. And you need to just absorb the information from the screen and answer directly. Now, if you like this video and if you'd like to support this channel, please enroll in my Solutions Architect course on Udemy. Part 1 and Part 2 Solutions Architect Associate courses are recommended if you are transitioning to the cloud and need a structured, hands-on introduction to AWS. The practice test course is recommended if you are already familiar with AWS, but you want to assess the gaps and prepare for passing the certification exam. I provided the links to the courses in the description. I hope you like this video. Do like and subscribe to my channel. Thank you.